Okay, we're back to talk about circular motion and centripetal force. Those kind of refer to the same thing, but the point is we're going to be dealing with objects. So far we've talked about objects that move in straight lines. We've talked about objects that move in parabolic fashion, like with projectile motion. One of the things we haven't talked about yet is objects that are forced to move in circles. So we're going to talk about why an object would move in a circle and what the consequences of this are. So many objects don't move in straight lines and move in curved paths. The easiest of these to analyze is circular motion. And to start off, we're going to link back to our last unit on gravitation. We're going to take a look at planetary orbits. So as you probably know, the force that keeps planets moving around the sun is the force of gravity, Fg. Okay, we just spent the entire last unit talking about the how we can calculate that force of gravity between the Earth and the sun. So I have the Earth here, and I want to draw in what direction the force of gravity acts on the Earth. Obviously, it attracts it towards the sun, so I'm going to draw it in this direction, Fg. And let's say that that's the only force acting on the Earth, okay? It's certainly one of the bigger ones. Let's say it's the only force acting on the Earth. If that's the only force acting on the Earth, then it also stands that since Fg would therefore be the net force, the acceleration of the Earth is also in this direction. So notice I'm not drawing a free body diagram here, okay? A free body diagram only has forces on it. Right now I've drawn two vectors, one for a force and one for an acceleration. So this is not a free body diagram. If this were the case, if this was all there was to it, then what would happen to the Earth? Well, it would accelerate and speed up and speed up and speed up until it hits the sun. By the way, this obviously isn't to scale. And then it would crash into the sun, and we wouldn't be here. Well, the Earth has been going around the sun for 4.5 billion years, and that hasn't happened yet, so there must be something else going on. And that something else going on is that the Earth is not moving at this spot. It would accelerate in towards the sun if the Earth wasn't moving, if it was at rest right in this position. And that's not the case. The Earth has some velocity, and it has some velocity tangent to its orbit. That basically means if you think of a circle that has a line touching it at only one spot, like the line doesn't intersect it at two places, it only intersects it at one, like it just kind of touches the edge and then moves off, that line could be said to be tangent. So when we think of the velocity of the Earth, it's not moving necessarily towards the sun at this point, it's not moving away from the sun, it's moving kind of perpendicular to this line between the Earth and the sun. So we say that you can refer to that as tangential velocity, or just velocity. So let's talk about what would happen if the Earth only had that velocity. If I cover up the force for a second, if this force didn't exist and the Earth just had this velocity, it would move off in this direction forever. There's no reason, if the sun wasn't there and this force didn't exist, the Earth would just continue moving in this direction. Newton's first law says an object in motion will continue with that motion unless acted upon by an outside force. So here's where we're at. If the Earth didn't have this initial velocity, the Earth would accelerate in towards the sun. If the Earth didn't have this force on it and this acceleration towards the sun, it would continue off in this direction. So since both of those actually do act on the Earth, what ends up happening? Well, it kind of takes a middle path, and I'm not saying it goes exactly diagonal. What's going to happen is the Earth is going to move to the left, but it's also going to start accelerating down. Notice that right now you could say that like the component of the Earth's velocity in the direction towards the sun is 0. Okay, towards the sun, this line right here, and the line showing the velocity, they're at right angles to each other. So imagine if you split up this velocity up into components with the vectors, or with the components, one points this way, one points this way. At this point, there is no velocity towards the sun, but it is accelerating towards the sun, so that's going to change. The Earth is primarily going to move to the left on this picture, but it's also going to start moving down a little bit towards the sun. So its path looks a little bit like this dotted line. Okay? Notice that as more time goes on and the Earth moves farther, it starts to move more and more down towards the sun. Let's take a look at what happens to the Earth when it's here. At this location, the Earth has been moving in this direction, okay, at this point. So I'm going to draw in the velocity vector. But there's still a force on the Earth from the sun. That's going to point in this direction. And, again, since that's the net force, the only force acting on it, the acceleration will be in this direction. And notice that we've kind of got the same deal going on. We've still got the velocity and perpendicular to the force of gravity and the acceleration. So what do you think is going to happen? If the force didn't exist, the Earth would move off in this direction. If the initial velocity wasn't there, the Earth would accelerate towards the sun. We're going to take kind of a middle path. This dotted line shows that the Earth primarily moves in the direction of the velocity at this point, but it also starts to accelerate and move in the direction towards the sun, which means its path is kind of curved like this. So once again, we have a force of gravity pointing in this direction, an acceleration pointing in this direction, and at this point, the velocity is downward. Okay? Look at how that changed. Initially, we had velocity to the left, and because of that force, we now have our velocity pointing downward. But not only did the velocity direction change, the direction of the force and the acceleration also changed. And I bet you can predict how this is going to look as we keep going around the curve. I'm just going to fill in the rest of this. It's a pretty easy pattern to spot once you get the hang of it. Again, you just keep want to be rationalizing, why would it move in this direction? At this point, the Earth feels a force from the sun kind of upward. The acceleration, therefore, is also upward. But the velocity at this point, the Earth is moving to the right. So the Earth is primarily going to move to the right over the next few bits of its motion, but it's also going to start accelerating up. And this story holds all the way around the Earth's orbit. And I bet you can guess where we're going with this. Where do you think the Earth is going to end up? Okay, a couple more to draw. At this point, the Earth is moving up. And we get back to where we started. So before we talk about the direction of the vectors, let's just write down, once and for all, why did the Earth follow a path like this? Well, if we just looked at the velocity of Earth, in this case, always points tangent to the circle, to the orbit, I should say. Orbital path. And it also was perpendicular to a line, an imaginary line that we didn't draw in, between Earth and Sun. And the net effect of this was that the velocity was always trying to, I don't want to say that, I don't want to mislead you and make you think that velocity is like a force, but the velocity tends to move the Earth away from the sun. Okay, and again, tangent just means if we had a line that only touches the circle in one spot, that would be a tangent line. And notice the velocity always falls along a tangent line. All right, so that's what the velocity did. On the other hand, the force of gravity on Earth is directed towards the sun. So the acceleration also points towards the sun. And the acceleration is trying to move the Earth towards the sun. What ultimately ends up happening is that these two effects kind of balance each other out, and the Earth ends up following a circular orbit. Okay, so we see why the Earth follows an orbit as it does. This is not just the case for Earth in an orbit, though. Okay? Gravity is not the only force that makes objects move in circles. I want you to answer these three questions. What force makes an object that's tied to a string move in a circle if you twirl it around? So imagine you have an object on a string, you're twirling it around above your head. What force makes the object move in a circle? Now, some people might say your hand, to which I would say, is your hand actually touching the object? No. The object is not touching your hand. The object is touching a string, which is controlled by your hand. But what object is directly in contact, or what is directly in contact with the object itself? It's the string. The string makes it move that direction. And we call the force that arises from a string attaching things tension. If there was no tension in the string that is tied to the object you're spinning around, then the object wouldn't spin around. What force allows a car to drive in a circle? Okay, if you're driving along a curve or in the road. Well, I want you to imagine this. What would happen if there was no friction between your tires and the road surface? Would you be able to turn? No, imagine it's very icy. When it's very icy, there's not a lot of friction, and what happens is sometimes you can't take a turn the way you want to, and you end up sliding through the turn. You go more straight than you normally would. The fact that that happens when there's less friction makes us believe, and it's true, that friction is what actually allows a car to drive in a circle. The force of friction is what helps you turn. You want friction. We always think of friction as this bad thing. You want friction to help you to turn. What force makes you move in a circle on like an amusement park ride like the Roundup? Okay, this is the one where you stand against the wall and then it starts spinning around and then it starts spinning like vertically, but you're pressed up against the wall. Well, if you're pressed up against the wall, then the wall is pushing on you, and that wall is actually pushing on you towards the center of the circle, just like FG was in this case for our object that was for the Earth as it moved around the sun. So it turns out that in this case, the normal force is the force that points towards the center of the circle. And notice that the force that's making the object turn always points towards the center of the circle. Okay? It's not pointing kind of diagonally like some people think. It's pointing towards the center of the circle. When you have an object on a string and you're spinning it around, the tension in that object is pointing towards your hand, which is at the center of the circle. The friction is and I guess you can't really see this one, but the friction on your car points towards the center of the turn, and the normal force on you on that ride pushes you towards the center of the ride. So all of these forces, they're all very familiar forces. They're all pushing you towards the center of the circle, and they're all the reasons that you would turn. Imagine if your back was not up against that paneling on the ride, or that paneling fell out. You would not have any reason to keep turning with the machine. You would go flying off it. There would probably be a lawsuit involved. So these are all familiar forces. The only difference now is that they're acting in such a way that they cause objects to actually move in a circle. When an object moves in a circle, we have a very special name for the net force in the direction towards the center of the circle. Okay, and that's what matters here. When an object moves in a circle, the net force in the direction toward the center of the circle is known as the centripetal force. Okay, centripetal force. And I guess you can remember that as you have NET in here, or I guess you have N and then later on ET. That's not scrambled up. You can see, excuse me, you can see from that it has the word net. It has the letters for net right in there. The centripetal force is not a new force, okay? It's just a fancy name for the net force. and we only use it when we're dealing with objects that are moving in circles. Since it's not a new force, it's not like a new type of force, it just means net force when we're dealing with circular motion, it does not go on any free body diagrams. I see people try and do this sometimes. They try and add an FC, that, by the way, FC is the symbol for centripetal force. They try and add an FC in there, okay? And that would be wrong. You don't ever put net force on a free body diagram. You draw the forces that are actually acting, and you sum them up algebraically to find the net force. Well, same thing goes in circular motion. You're not going to draw a vector on a free body diagram that says FC. What you're going to do instead is label the vectors with whatever force they actually are, and the algebraic sum of those vectors is the centripetal force. Okay, and we'll get to some examples and we'll kind of see how this works. There's an equation for Newton's second law. Remember, Newton's second law is F net equals ma. There's an equation for this in circular motion. It's really the same thing. It's just got a couple of different subscripts on it to help you remember we're dealing with circles. Newton's second law for circular motion is given right here. Fc equals ma. Fc is the centripetal force. Remember, that just means net force. M is the mass, and actually I said it wrong. It's Fc equals mac. Notice that AC is centripetal acceleration. Okay, it's the acceleration of an object as it moves in a circular path. So Fc equals mac. So if we're dealing with an object in circular motion, this is what you want to go for when you're dealing with the net force and the acceleration. Now, there's a couple different types of ways things can move in circular motion. Sometimes you have an object that is moving with a constant speed in circular motion. We're just going to put a note over here. This has a special name. This is called uniform circular motion. Uniform in this case means the speed does not change. Okay? So it happens that sometimes an object's speed can remain constant, but the speed just tells us how fast something's moving. The direction doesn't matter. Quite obviously, as you can see from the picture that we drew earlier, if something's moving in a circle, the direction is always changing. So that means that the velocity must always be changing. So while its velocity changes because the direction the direction the object moves in is always changing. Okay? So think about this. The speed is constant. Usually when we see speed constant, we think no acceleration. But the direction is changing. And because the direction is changing, that means an object in circular motion is actually accelerating. So we've got to get the old idea of accelerating, meaning speeding up and slowing down exclusively, out of our heads. Remember that the third way something can accelerate is if it changes direction. Because if it changes direction, the direction of the velocity is changing, and acceleration is change in velocity over time. So if some part of the velocity is changing, in this case the direction, that still counts as acceleration. So when an object in circular motion accelerates, which all objects in circular motion, by the way, are accelerating. There's never a case where something is moving in a circle and it's not accelerating. We have a specific name to refer to this. We call this centripetal acceleration. AC, like we just saw up here. And there is actually an equation for calculating AC, the centripetal acceleration. I could go through the derivation, but it takes a little bit more time than I want to right here. The centripetal acceleration of an object is given by v squared over r, where v is the speed, we have to square it, and then we divide by r, which in this case is the radius. Okay? AC equals v squared over r. And you can take a look at the front for this last part, but just to refresh, what direction did all those vectors that we drew, what direction did they all point in consistently? Okay? In this case, remember we said that the force of gravity was like the net force, so therefore it's also, if it's the net force, and we're talking about circular motion, it is the centripetal force. And notice that Fg always points in towards the center of the circle. Well, that tells us that the centripetal force will always point towards the center of the circle. Notice that the acceleration, really the centripetal acceleration, always pointed in towards the center of the circle. And the velocity always pointed tangent to the edge of the circle. So here's what we have. The centripetal force always points in toward the center of the circle. Okay? Sometimes people like to think that the centripetal force points outward. That's wrong. If we had something that pointed outward, we would never get an object moving in a circle. The centripetal force, the net force for something that is in circular motion, is always directed inward. Because it's directed inward, we can get the turning, okay? Because we have to direct it inward in order to have this object turn and move in a circle. The centripetal acceleration, therefore, is always also in towards the center of circle. And the velocity of the object always points tangent to the circle, which is interesting because what this means is that if the centripetal force were to go away, if this force were to suddenly not exist, this object would not continue moving in a circle. It would shoot off in this direction. If the centripetal force, Fg, simply ceased to exist right here, this object would move tangent to the circle. Same thing here and here. So if the force goes away, the velocity will simply keep the object moving in whatever direction it was last in. Okay, because now there's no more force, because there's no more centripetal force, so there's no more reason for it to move in a circle. That's it for that notes. We will do some examples in our second video.